measure complexity and, to explain, the rationale. If the response is local, no integration, it's easy to zip. If it's global, but there is no differentiation, it's very redundant. You don't need a lot of information to zip it. It's like when you zip images. If the response is rich and global, then you have hard time compressing it. So this is the idea, right, of the zipping. And you come up with one value that is compressibility, if you want. It's called technically algorithmic complexity. And then you plot the value, and these are a reference scale based on the measurement we did in patients subjects who are able to report. And then based on this distribution, you can draw an operational cutoff. And the idea is that if you have a complexity that is high, is in the range of the conscious benchmark, then even though the patient is unresponsive, there must be something there. So when you test it in patients, it works very well in minimally conscious patients. These are patients where consciousness is fluctuating, very difficult to detect, and we have a very high sensitivity. But then what is most important, we can draw inferences in the patient where you have nothing to say behaviorally, vegetative state patient, the one that are fully unresponsive. And here it's interesting to see that you can stratify them in low complexity patient, the majority of them, but then 20% of vegetative state patients, they have internal brain complexity in the circuit that is comparable to the one of the conscious benchmark. So here, the inference is that there must be some kind of disconnected conscious, or at least you have to treat them like this. So this is it's interesting, but what's most important, I think, is that within and beyond HBP, we are all converging on this idea that complexity matters for consciousness. So these are works from Paris, from Liège, beautiful works, and also from groups outside of HBP, suggesting that really the best way for the moment to assess consciousness based on brain-based measures is this measures of integration, differentiation, information sharing, or complexity, all revolving around the same concept. And I think this is very encouraging, and we are in a good place here. In practice, what do we do when we have such measures? So take two patients that are non-responsive, so they're behaviorally identical, and with a measure based on brain circuits, you can open the black box, and maybe you find patients with high complexity, and here that there must be a potential for consciousness, and what you can do in these patients is to restore channels of communication, assuming that there is consciousness there, and you can do this with brain-machine interface, and Peter will talk more about that. And in these patients, instead, on the right side, where you have low complexity, well, this is a challenging, proposal, but what we need to do is to restore complexity whenever possible. Okay. This is important.
Okay. I need to ask you to slowly round up, but I will. Go ahead.
I'm done. This is important because, some patients are stuck in low complexity, other recovers, and we need to understand what are the keys to turn the neuronal mechanism. And this is, what we do in HBP now, in this third phase of the project. So we have collected data about, why complexity is fade and recovers, about the neuronal mechanism at different scales, from slices to animals to humans. And now we have to combine this, taking advantage of the eBrain platform, into models in order to have predictions about what are the manipulations that we need to do to restore complexity. And we have already two ideas, about mechanisms that might play an important role. One is silencing the neurons by stability, the new tendency of neurons to become silenced. And another one is dendritic decoupling. This is discovered by Matthew Larkin within HBP, and it's a very interesting idea. So I think that working on this, we can make a difference for consciousness science, but also for clinical applications.
Thank you. And as I said, I am an interested non-specialist, and it sounds critically important. And I'm going to say, silly, without making light of this in any way, all of those Hollywood films, when you see people, waiting by bedsides and fingers to move or eyelashes to flicker, what's so fascinating, and what you're explaining in these measurements is you're going way above that. I mean, it's so important. Tell me, what are the general implications? If you had to sort of sum it up, what are the general implications for your work within the project?
Yeah, so you give me the opportunity to pull up this figure that I like a lot. So this is a figure graph by Christoph Koch originally, which says that, for the moment, we assess consciousness based on what we can observe from an extrinsic perspective of function, intelligent behavior. This might work in nature, but we are changing nature. So we have these patients which are disconnected and by the point of view of intelligent behavior, we cannot observe much. And then we are building machines that are very functional, very intelligent, and they're becoming more so, like AlphaGo and others. And this is becoming challenging because, we can miss consciousness where this is present, or see consciousness where it is not present, going back to what Mavi was saying. So we need to work more on this axis, on the y-axis, finding better measure of consciousness above and beyond function. So I think this is a major challenge that we have, and which has also a cultural value in general, an educational value, developing a sensitivity to consciousness.
And just as a close, which is important, we do talk medical use cases. So if we're talking about disseminating into a clinical setting, very short, what sort of time frame are we looking at for that?
Well, I think we are now changing, these techniques are quite complicated for the moment. TMSEG should be developed towards a more, easy technique like ultrasound echography, bedside measure. We are working towards that. I see 5 years to develop that, but also all together in HBP and beyond HBP, we should develop a pipeline, a workflow, putting together all the best measures that we have developed for better diagnosis, prognosis, and treatment. And we are working towards that, really.
Thank you. Now, Marcello, there's been a lot of questions coming in as you've been speaking. So what I'm going to do is I'm going to let you take a back seat, and then you can have a chance to look at the private chat, because you'll see some of the stuff that's coming in. So you can have a look at that, and I will introduce our next speaker, and then I'll have some questions for you afterwards. But thank you so very much, and for condensing all of that into such a short time. I know it's not easy. So thank you. We will hear more from you shortly. Okay, so while my is relaxing, I'm going to invite our next guest speaker to come and present, and then I will invite both Marcello and Mavi back for a chat. So I'd like to now invite to join me Peter Roosema, the director of the Netherlands Institute for Neuroscience. So if he could come on screen. Hello, sir. Very nice very nice to see you again. Now, when we had a chat before this webinar, and I was saying, what's a good way to describe the link between Marcello's work and yours, and you suggested that he's the kind of the bystander, because he's reading from the brain, and he's trying to develop tools to pick up consciousness where there is some doubt, whether there is any. You're not reading from the brain, you're writing to it, creating conscious perceptions. So can you tell us more about that work, how you calibrate computer-brain interfaces to ensure electrical stimuli inputs reach the level of attention? Thank you very much. The floor is yours, sir.
Yes, so...
voila, I can see your screen. Great. Okay, go ahead.
Yeah, so today I would like to talk about how a stimulus may reach or may not reach consciousness, and the same stimulus sometimes makes it and sometimes doesn't. And I would like to talk also about the potential application of these findings. So in the world, there are about 40 million people who are blind, and many of those will not benefit from treatment in the eye because the connection between the eye and the brain is lost. So for those people, a logical approach would be to make an interface with the visual cortex, and people have started working on that, and that's also what we're working on in my team. And if you stimulate electrically a group of neurons in this region of space, actually it's what we call retinotopy, so it's basically a layout of the entire visual field in the visual cortex. If you then stimulate one of those at one of those locations, one group of neurons, a subject, and it can also be a subject that has been blind for a number of years, will see a dot of light, and it will be a dot of light at that location in the map where you're stimulating. Now the goal is to have many electrodes there, thousands or even more, so that you can create thousands or more dots of light at different spatial locations. Okay, so and now you can work with this like a matrix board along the highway. If you switch on one bulb on the matrix board, subjects will see a dot of light, but you can also create a pattern by switching on some of these electrodes. Okay, and that's the eventual goal, a goal that scientists have long had. Now, this is the system that we would really like to build. So there will be a camera that takes in images from the outside world that then needs to be translated into brain stimulation patterns that should be meaningful, as you see here. They then need to be transferred to inside the brain. So there should be a brain chip that then talks to electrodes that are going to electrically stimulate the neurons. Okay, so that's the system that we want to build. Now, the thing is that if you stimulate with a very weak current, you are in a situation where the stimulus may or may not reach conscious awareness of the patient. Okay, so this is an important question. And a few years ago, we carried out a study where we looked at that issue. And here we first started with visual stimuli. So all the audience, I would like to invite you to look at this red dot in the middle of the screen. And what I'm going to do is to present to you a stimulus that sometimes can be very weak. So now I'm going to present the stimulus, 1, 2, 3. I suppose that most of you saw the stimulus. Now I'm going to do it again, 1, 2, 3. Okay, so now it was more difficult. Try it again, 1, 2, 3. And the last time, 1, 2, 3. Okay, now my suspicion is that many of you did not see all these stimuli. And what we found in this study is that if you present a weak stimulus over and over again, sometimes if it's close to the threshold for perception, sometimes it will, and sometimes it will not reach consciousness. So what happens here? So what we found is actually that the difference is well explained by a theory that was proposed by Stanislas de Hane a couple of years ago, who called this theory the global neural workspace theory. And what happens here is that if you present a weak stimulus, it needs to be propagated to higher areas of the brain in a sufficient strength. Now, if you do so, then there is a process that he called ignition. And ignition actually causes a reciprocal interactions between different brain areas, such that if you take the stimulus away, it's a very weak and brief stimulus, that the activity pattern is upheld through these interactions. We call it a working memory. Okay? Now, if you now present the same stimulus, in some conditions, it may not reach the higher areas in sufficient strength. Okay? If you then take the stimulus away, it will fade out, and it will not be perceived. It will fail to reach consciousness. If the same stimulus, and that is due to the noisiness of the brain, kind of makes it out of the noise, then it can reach the higher areas, and it can cause ignition, causing this working memory trace. Okay, so this is background knowledge that we can use in the design of a visual cortical prosthesis, because we're also stimulating these brain cells very weakly. And we're testing this now in monkeys, and we implanted in the monkeys more than 1,000 electrodes. This is what it looks like. So here are all the electrodes. Each of these squares actually corresponds to 64 electrodes. And we're now going to stimulate in primary visual cortex, the first cortical stage of visual information processing, in recording from the next higher areas to see whether what we stimulate here, whether it's strong enough to cause conscious perception. Okay. Now, what we do here in this graph, on the x-axis here, we're stimulating with different current strength. And here on the y-axis, you see the hit rate, the probability that the monkey perceived the stimulus. And you see that if we stimulate strongly enough here, in this case with 20 microamperes, the monkey always sees the stimulus. If you then reduce the strength of the stimulus, there's a threshold here, 12.6 microamps, and then the animal reports it about 50% of the time that we give the stimulus. Now, the interesting thing is we also had electrodes in a higher area V4, to which we could record. And what we observed is that if you give weak stimuli, we basically see no activity in area V4. If we give stronger stimuli above a certain threshold, then we start to see activity in area V4. And the interesting thing is that the activity in V4, as a function of the current level, resembles the perception. So if we give about 12.4 microamps, then the activity in V4 is basically half maximum. So we can basically use the activity in V4 to see whether the stimulus is on its way to reach conscious perception. That's very cool. Now, another important question is, if you then stimulate one electrode, the animal is seeing a spot of light. What happens if we stimulate a pattern of electrodes at the same time? So to find out if the monkey then perceives a pattern, we trained the animals to report 16 letters of the alphabet. Okay, so we present the letter D. Now, you can't ask the monkey, what did you see? So we had to train the animal, and we trained him to make an eye movement into this choice display. Okay, so if the animal saw letter D, we expect him to make an eye movement to the letter D in the choice menu. And now the critical experiment is we're not going to present this visual stimulus anymore, but we're going to stimulate a pattern of electrodes, okay, aiming to recreate a letter by directly interfacing with the brain, hoping that the animal will report the corresponding letter. Okay, and this is the result of this experiment. All these green dots are locations where we can create a single spot of light, of phosphine, but now we're going to stimulate multiple electrodes at the same time, trying to create a letter. And the blue dot is where the animal directs his eyes. We try to create.
You have a minute?
Yeah, I'm almost done. So here,
It's okay.
the electrodes are stimulated in the shape of a letter A. Now it's an L. It's a T. Okay, so this is very exciting to us. It's the first time this has been demonstrated that pattern stimulation of the visual cortex can give rise to pattern perception. Okay, so this is an important step towards this dream of creating an interface with the visual cortex of blind people. And we hope to be able to go into humans in 2023, although don't be too angry at me if he can't make this work. Okay, so what we demonstrated here is that variations in consciousness of weak stimuli are related to failures of propagation from lower areas to higher areas. And this knowledge will help us in the design of a visual cortical prosthesis.
Thank you. Thank you. And I was only giving you time signals because we have so much activity in terms of questions. I have one, and then I'm going to invite your colleagues back. I mean, so clear the end result, the importance of your work. That's critical when we talk about practical applications and medical use cases. But there's a science fiction element, isn't there? Of course. I mean, if we're talking about putting AI between a camera and a brain, and I talked ethics with Mavi at the outset, what do we need to be careful about? Should we be wary?
Yeah, so there's definitely an ethical dimension here. So there have been patients that have been implanted with electrodes in the visual cortex. And the simplest thing you can do is simply look for contrasts and present the contrasts in the visual field, actually on the brain, where they are being detected. That's a very simple algorithm. But you can also make it more sophisticated. Suppose you're a user of the prosthesis and you want to cross the street. You don't want to see the trees, you want to see the vehicles, right? So then you might only want to select those electrodes that correspond to vehicles. It can be useful, but of course there's an ethical dimension here because now the algorithm is deciding what the subject will perceive and what not, right? So therefore it's also useful to have these ethicists on board within the Human Brain Project.
Thank you very much. And as I see, people are rife with activity and interest. So let me please ask Mavi and Marcello to join us. That would be fantastic. Now, I am going to, in a second, open up directly to questions from the floor, but I just want to give Mavi a chance to in a nutshell, come back. You said, within the project, you focus on these two aspects of consciousness. They're measurable. We've just heard about the concrete examples. Anything else that you wish to comment on in terms of those medical use cases or the practical applications? Anything important for our audience to understand?
Well, I think it's very important. You were asking me before, consciousness sounds slippery. How do you grab this? And we have seen two very concrete medical applications of consciousness studies, but something that I find very relevant is that they are very closely linked and very connected to the basic research, both of them. And I think this is very important because it's an excellent example of how basic research translates into medical applications. And also the fact that by the application itself, we learn more about how consciousness is generated and how it functions. So the application gives us also basic information. I think you are muted.
Sorry, I just, as you said that, I saw it. I'm so conscious to not let my paper shuffling into